Alright, so here's section 4.6, Arithmetic Sequences. Let's say Mr. Callan wants to create a pyramid display with all of his Star Wars memorabilia. And at the top, he just wants to have just one item. So there he is, Darth Vader up here at the top. And then each row underneath this is going to have two more items in the row above. So you can see the next row has three different items. And because 3 is 2 more than 1. And now my shelf can hold, shelf can hold a total of 4 rows. How many items will be on the bottom row? Well, this isn't too hard to figure out. We'll just keep on going. We've got 1 here, 3 here. That must mean we need 2 more than 3, which would be 5 on the next row. So now you can see that there's 5 there. And then that's our 3rd row. 4th row must have 2 more than that. So that would be 7. And so there you have it. The bottom row has, as you can see, 1, 2, 3, 4, 5, 6, 7 total items being displayed. So, not too bad there. We're just kind of following the pattern. In the first row, we had 1, and then we had 3, then we had 5, then we had 7. So just a quick pattern to follow. What if it involves a little bit more work? What would we have to do then? Let's consider what could happen if Mr. Callan's shelf could hold 17 rows of toys, which is quite a few toys, but he loves Star Wars. Now the question is how many items would be on the bottom row? Well, we can use some algebra to help figure this out. Let's start by looking at a scatter plot which compares the number of shelves with the number of items on each shelf. So if I look at this coordinate grid, you can see that I have the number of rows on my x-axis, the number of items on my y-axis. The first row had 1 item, second row had 3, third row had 5, and the fourth row had 7. And so if I look at this scatter plot, what I notice is it actually is completely linear. This relationship is really nice because of the fact that I'm going up at a constant rate of change. For an arithmetic sequence, that constant rate of change is going to have a special name, and it's called the common difference. The common difference is basically the same thing as slope, except it's what we use to talk about with sequences as opposed to lines. So even though this is a linear relationship, if we were to connect these points here, it's not really a line, it's a discrete graph, and so we certainly wouldn't want to connect all these points. So the common difference here, we'd calculate a very similar way to the way we would find the slope, and it has to do with the vertical change, or the change in the y, in this case the change in the number of items, as compared to the run, which is the change in the number of rows. Well, because our run is 1, and it's always going to be 1, 1 to 2, 2 to 3, 3 to 4, we're really only interested in the rise, and we're basically thinking about how much do we go up by each time. Well, we know the rule is we go up by 2 each time, and so our common difference is 2. Now, it's possible to have a common difference that's negative, in which case our common difference would be result in us decreasing each time. But in this case, we're going up each time, so we're increasing. We have a positive common difference. We also have something that's important called our starting point, which is our first term. And the first term we refer to as A1, A referring to the arithmetic sequence here. And so what we have to do is we have to figure out where our starting point is. Well, it's pretty clear. That's just going to be 1. And that comes from basically the y value here. We started with 1 item on the shelf. Our second term would be 3, third term 5, fourth term 7. If we write these out as a list, 1, 3, 5, 7, we can see that we're going from one term to the next by the common difference. 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 2 is 7. So this is the pattern we can use to help answer the question of what could happen if we're holding 17 rows of toys on this shelf, just to figure out how many are on the bottom row without figuring out everything else in between. So we have this really nice formula, and this is an important formula to learn. It says a sub n equals a sub 1 plus n minus 1 times d. Right now, it doesn't really look like it makes a lot of sense, but once we see an example, I think it will. A sub n is the nth term in the sequence. Well, we're looking for how many toys can fit on the 17th shelf. So we're really looking for a sub 17 is what we're looking at here. And a sub 1 we know is the first term in the sequence, so in this case that's 1. Plus n minus 1, well, n in this case is the same n from my subscript on my a, so I'm looking at 17 minus 1. And then d is the common difference, which we saw was 2. So now I can actually just go ahead and simplify this. So that's 1 plus 17 minus 1 is 16 times 2. That's 16 times 2, which is 32. And 1 plus 32 is 33. So a sub 17 equals 33. That means I can fit 33 toys on the 17th row of this display. That is quite a few, and not the least bit embarrassing. But that's how you do it. That's all that you have to do. You just plug in by using that information right there. If we wanted to have a general formula, we could just plug in for the common difference and for a sub 1, and then we would have that general formula we could plug in at a later time. So let's see an example using that. So here are two examples we're going to try. We're going to do the top one first, and I'm going to start by writing just the general equation, and then I'm going to plug in to find the desired term. So the first one, I know my first term is 8, my common difference is negative 2. I said I could always have a negative common difference. So I'm going to start with my general formula, which is a sub n equals a sub 1, that's my first term, which is 8, plus n minus 1, that stays as n minus 1 for now, times my common difference, which is negative 2. I'll now distribute the negative 2, so a sub n equals 8 plus negative 2n plus 2. And then just rearranging this, I get negative 2n plus 10. And I think you'll find that actually looks a lot like slope-intercept form. Not surprising, since arithmetic sequences really look a lot like lines. So now that I've done that, to find the 10th term, I'm finding a sub 10. A sub 10 is looking at negative 2 times 10 plus 10, which is negative 20 plus 10, which is negative 10. So if I took a sequence that started with 8 and had a common difference of negative 2, the 10th term would be negative 10. All right, last one here. Let's say I know the third term is 4 and the fifth term is 10. Well, to figure out the common difference, I know that I'm going to be doing 4 to something is my fourth term, to something else, which is my fifth term, which is 10. Well, since that entire gap is a gap of 6, each of these little changes must be 3. That's my common difference. My common difference is 3. So you get to 4 to 10 in 2 steps. I have to be taking 2 steps of 3. Now to figure out the first term, I realized that my third term of 4, I could work backwards. And so if I kind of go from 4 backwards to the second term and backwards again to the first term, in that other direction, I'll be doing minus 3 each time. 4 minus 3 would bring me to 1. 1 minus 3 would bring me to negative 2. So the equation that I'd really be working with here, I'm just going to give myself some space, is a sub n equals a sub 1, which is negative 2, plus n minus 1 times the common difference of 3. And so then I could get the general form by distributing out and having a sub n equals negative 2 plus 3n minus 3, which is the same thing as a sub n equals 3n minus 5. Now to find the 9th term, that's a sub 9. That's all. So that's 3 times 9 minus 5, which is 27 minus 5. Oh, let's see if I can fix that up there. I'll just try writing that again. 27 minus 5, which is, of course, 22. And that's the 9th term in that sequence. You can write it out to check, but that'll get it for you. All right, so that's a quick overview of arithmetic sequences, and I hope that it makes sense.